Second lesson of 4, Unit 7. We are still going to keep our brains out of calculus, and we're still going to just be thinking about areas. In specific, we're thinking about these infinite sums, these integrals, and we're going to talk about the properties of these integrals, okay? So, this notation should start becoming familiar to you. The way we read this is the integral from a to b of f of x dx. And instead of integral, I could write infinite sum, right? Integral or infinite sum. Okay, so we're doing an infinite sum of a bunch of skinny rectangles with width that is infinitely small and then a height based on a function, okay? But we know that when we sum up all of these rectangles, these widths times heights, this really becomes the same as like the area from A to B between my function and the x-axis. Okay? Different ways to think about the same thing. The integral is an infinite sum, or it's really the area. And we kind of already discussed this. Now, what's really important is that this A to B, this order matters. We haven't really discussed that until today. You've been used to having the smaller number down here and the bigger number up here for a reason, but if we flip-flop them, it would change things. These D's, there we go, order matters. So in your integral, what is down here is where we are going to start. The bottom number is your starting point. The number up at the top here is your ending point. Your finishing point. Okay, and we've dealt with going from left to right already. If this is A and this is B, and I'm talking about the area from A to B, when we are above the x-axis, and if this is F in this red line, we know that this area is positive. Why is it positive? These function values of all of these skinny rectangles have heights that are positive, the function values. And then our dx's, our widths, since we're going from left to right, these dx's are also positive. We're moving in the positive direction on the x-axis. Okay, so we have a function value that's positive, a width that's positive, area above the x-axis is positive. Okay, we will see how that changes if we go from right to left. If we are below the x-axis, well, yes, we always consider area to be positive, but this is kind of different. This is an infinite sum of these rectangles. Well, these rectangles down here have negative heights. And our width, since we're going from left to right, remain positive. So this is why we kind of consider this area between the function and our x-axis. We consider this to be negative. Well, it is. It's not that we consider. That's what it is. So the function values are negative, but the widths remain positive. Well, let's go from right to left. Let's go from B to A. So again, this up here, A to B, this is left to right. Well, let's go from B to A. Now I have this B and this A flip-flopped. It is not the same as A to B. So here we're going from right to left if B is to the right and A is to the left. Okay, let's see what we have. So if I'm doing an infinite sum of a bunch of rectangles starting from B going to A, and I'm above the x-axis like this situation, well, these rectangles I'm creating, they still have heights that are going to be positive. But these widths, these dx's, these infinitely skinny widths, since I'm going from right to left, that is going in the negative x direction. Since that's a negative x direction, we consider this width to be infinitely small but negative. So all of a sudden, it's a positive times a negative. This is a negative value. So above the x-axis from right to left, actually the area is considered negative. Let's see what happens if we go below the x-axis from right to left. Well, the function values are negative for these rectangles, these infinitely skinny rectangles. But the widths of the rectangles also are considered to be negative since we are headed in the negative x direction. So this is actually positive. So what conclusion can we make? The areas from the right to left are what compared to the areas from the left to right? Opposites. Opposites is the key. Right to left is opposite the area from the left to right. If you want to use integral notation, you could say the area from A to B is opposite the area from B to A. Okay? Order matters. Order is important with these infinite sums. Okay? So that's the first kind of property that we need to know. And all we're going to do is just more and more properties of these integrals. Here's another one. It's the integral from A to A of f of x dx. So the infinite sum starting at A, going to A of f of x dx. Skinny triangles of height f of x and skinny width of dx. So instead of from A to B, all of a sudden I'm just going from A to A. Right? A and A are on top of each other. What do you think this infinite sum is? Mr. Meyer? You'd think it's just the height, but remember, we're talking about rectangles with heights and widths. What's the width of that? 0. Exactly. So the height here is the height at f of x. It would be f of a, right? But then the width is 0. Turns out we would say the area from A to A is just 0. You think about that not as an infinite sum, but by areas. Think about the area from A to B. Well, it'd be getting smaller and smaller and smaller and smaller and smaller and smaller, infinitely small, no area. Cool. So that's another one. Now let's take a function and let's multiply it by a constant. So the integral from A to B of k f of x dx. K is a constant. And then I give you a picture of a function and then a function times 3. And I'll give this some function values. We'll say this is 1. We'll say this is 4. we'll say this is 2. Okay, so I'm going to use this example to help us discover this property. So first, let's find out the area from 1 to 4 between f of x and the x-axis. We can calculate that. What is this area? 4. It's a triangle, width 4, height of 2. This area is 4. Okay. Now, I will take all of these function values and I'll multiply them by 3. This is our kind of transformed or rotated function. So everything gets multiplied by 3. So what was 2 becomes 6 up here. And we have a new triangle. So what is the area from 1 to 4 under 3 f of x dx? Let's see, we have a triangle. What is this area right here? We have a triangle of width of 4 and a height of 6. What does that equal? 12. Well, what's another way to figure out that area? Multiply your original area by the constant. It's just 3 times your original area. Seems obvious enough, and it is for this one. So this property, if you have a constant times a function, you could just pull out the constant and find the area of the function. This is our next property. Okay, so we multiplied functions by constants. What if we add constants to functions? What if I take every single function value, instead of multiplying it by a value, I add values? I add 3 to this function. Well, if we have an example, maybe that'll help. Let's start by calculating this area. That's not A to B. Let's go from 1 to 4 under just F. Is it going to be a decimal? That's 3. It's going to be 4.5, right? Why don't we make this 5 so it's not a decimal? Okay, let's calculate this area first. Well, let's see. We have a trapezoid, base of 4, so it's 1/2 times 4 times the sum of my heights, 1 plus 2. So that's 2 times 3, that's 6. All right, let's find the area from 1 to 5 of f of x plus 3. So what was 1, 1 becomes 1, 4. What was 5, 2 becomes 5, 5. What do we get for that? Everybody write it down on your paper. Do some work today. What is the area under f of x plus 3 from 1 to 5? I found out that the area from 1 to 5 of just f of x was 6. F of x plus 3, 18. Thank you. Not 9. It's not 6 plus 3. So this is kind of different. This is not very, easy. Well, here's another way we can think about this and another way we can figure out this area. I take this area and or take this function and I add 3. What happens is I carry this and the line segment. Grab the line segment, guys. I know, ungroup. Okay. I carried it up here. And all of a sudden, this area is right here. That's 6. What gets added? A rectangle. What's the height of the rectangle? K, 3. What's the width of the rectangle? The width of your interval. This is a rectangle that is a 3 by 4 rectangle. So here's how we can do this. This is the area from 1 to 5 under my function. That's the 6 plus a rectangle with a height that is K and a width that is the width of your interval. So that's 6 plus 12, that's 18. So let's write that using f of x and k and a and b. So it would be my area from a to b of f of x plus I would have a rectangle, I'll just write that there, with a height that is k times a width that would be the length of the interval, which is b minus a. Maybe I'll move that height and width up. There. Now this would go as well if you're subtracting a value. If you're subtracting a value, what you would be doing is subtracting a rectangle's worth of area. So you can make this plus or minus. Okay. Once we move into the connection between kind of calculus and these areas, there's another way to see this kind of rectangle's worth of area that I'll show you. Okay. So that's your next property. Next one. This is an easy one. This is an intuitive one. We have the integral from a to b of f of x dx plus the integral from b to c of f of x dx. So the integral from a to b, that's essentially the area under f of x from a to b. And from b to c, that's the area from b to c. What do we think this equals? Not c to a to c, exactly. Good. Makes sense. So this plus this gives you that. Okay? One more. The integral from a to b of h of x dx, where h, this function h, is a sum or a difference of two functions f and g. The area under this h, which is the sum of f and g, is just the area, or the integral, of the areas under the individual functions, either summed or subtracted from each other. And of course, you can just replace f of x plus or minus g of x there for h. Instead of having h, you can have f plus g. And you can just say, okay, I can split things up. If I have sums of a bunch of different functions, I can just split it up into integrals of individuals. All right, let's do some problems. Here is some given information up top, and then below will be 6 problems. I want you all to write down the given information, or at least look at it, and then all come up with the answers to these 6 problems. I'll give you a tough one here. All right. 1, 2, 3, 4, 5, 6. Ready, set, go. Once you get your answers, check with a neighbor. See if you're getting the same ones. Make sure we know that order matters. It's very important. More discussion, more talking, more help. We have some new students. Make sure we're looking out for the new students in our class. New students, don't feel shy for asking for help. I would try that one again. Try doing it, just do 5 to 7. Figure out what 5 to 7 is, and then just take the opposite of it. So don't think about the 7 to 5 yet. Don't think about anything crazy. Just do 5 to 7. So you got 3 plus what? Well, it's a -2, so a rectangle height that's -2 and a width of 2, right? So you got 3 plus -4. And that's from 5 to 7. Yeah. It's tricky, right? All right, the bottom right one's really tricky, right? We'll figure it out. Okay. Ms. Bush, did you get from 5 to 0 of f of x?
5 to 0. Wait, you're not giving 0 5 or -10.
Okay. All right. Ms. Slade, did you get 7 to 7? Mr. Brunn, did you get 0 to 7? This one. 13. All right. Ms. Gross, did you get 0 to 5 of f of x plus 3? Didn't get it. Mr. Durrett, did you get it? Can maybe help Ms. Gross?
I got 25.
25 is correct. How'd you get 25?
So you know the 0 to 5 is 10. So it's 10 plus 3 times the difference between 0 and 5. So 10 plus 15.
Okay. All right. Mr. Conwell, what about 7 to 5 of -3 f of x?
-3?
Wouldn't be -3 because you got -3 times.
Oh, I didn't see that part.
That's okay.
So 9?
So it would be 9, right? Because from 5 to 7, it's 3. 5 to 7 of this would be -9. The opposite of -9 will give me +9. This is how I deal with these backwards ones. I think of doing them from 5 to 7 and then taking the opposite of it. So that brings me to the last one. We got from 7 to 5 of f of x minus 2. Well, I'm immediately just saying, listen, let's forget about the 7 to 5 going to right to left. Let's just go from left to right, and whatever I get, I'm going to take the opposite of it. So I think from 5 to 7. Well, if this is 5 and 7, then it's just the area under f plus this rectangle that's going to be a height of -2 and a width of 2. So I have 3 plus -2 times 2, that's -4. So from 5 to 7, that area is -1. Well, from 7 to 5, that area is going to be +1. Okay? And the key is to think opposite of your normal one. Figure out your normal one first. That won't kind of confuse you too much. All right? Questions? Let's do some more. Integral from 2 to 6 of f dx is 10. Integral from 2 to 6 of g dx is negative 2. What's the integral from 2 to 6 of f plus g? And then what's the integral from 6 to 2 of g minus 2f? Check with the neighbor.
Does it matter which, okay, like it used to define 40 worked out? Like I just automatically thought 2 negative 10 times negative 2.
Yeah, and then you took the opposite of it afterwards. Yes, that's fine. Just do it at the end.
No, I did it beforehand. Because like I automatically.
Oh, okay, yeah. So yeah, as long as you're taking it, the opposites of all of them.
Okay.
One on the left should be standard. The one on the right, really, the best way I can think of doing the one on the right is just to think of the opposite from 2 to 6. So I'm going to do the one from 2 to 6 first. I'm not going to take opposites as I go along. I'm just going to do 2 to 6 first. This is 10 minus 2 times 10. Right? Oh, what am I getting? Yeah, this is negative 2. Sorry. Negative 2 minus 2 times 10, that's negative 22. So once I know that's negative 22, this has to be positive 22. Okay? Some more. The key is to do this one first. This one second. There should be dx. You all right?
What? Yeah.
I know.
Yeah.
Yeah. Okay, once I know that one, do the one over there on the right, bottom right. Anybody get the 1 on the bottom right yet? Yeah. Mr. Magnell, did you get it?
Probably wrong one.
What'd you get?
-7.
That's right. How'd you get that, Mr. Magnell?
Number 1 is 0 to 5, so you just subtract out the 3 to 5.
Exactly. 0 to 5 will equal 0 to 3 plus 3 to 5. That's the whole A, B, B, C. 0 to 5 is -5. 3 to 5 is 2. So what's this guy? This guy's got to be -7. Okay? Now, same questions could be asked here, okay, given a graph. This is like the graph on your quiz. You know, I might add in some f of x plus 2 and from 7 to 5 instead of 5 to 7. Okay, I might add a -3 in there from 5 to 0. So more kind of complexities keeping track of order mattering. Whenever you have something from right to left, just figure out what it is from left to right and then take the opposite of it. Okay? But that's it. Have a good weekend. I'll do these problems. They'll be on the video if you want to watch them. All right. 3 extra problems. This should look familiar. All right, I got f of x plus 2. So what happens is that this is going to move up to the top. So we'll have this negative area that will kind of move up, and then I'll include a rectangle of area. So the way I do this when I'm talking about something from right to left, I immediately flip it from left to right, and then I'll just take the opposite of it as my answer. So from 5 to 7, this area is a triangle. It's a 2 by 2, so this is -2. So from 5 to 7, this would be a -2. But since I'm adding a rectangle's worth of area, this would be adding a rectangle that is 2 by 2. This would be an area of 2. So 4 plus -2, that's 2. So if I go from 7 to 5, that's going to have to be -2. Okay? If I have a question that asks me the area under this function or between this function and the x-axis from 2 to 2, that's going to be 0. Doesn't matter what your function looks like. It's just 0. And then from 5 to 0 of -3 f of x. So again, 5 to 0, immediately going from 0 to 5 of -3 f of x. So 0 to 5, we have a trapezoid. Width of 2, so it's 1/2 times 2, and then height of 1 and 2. This will make this 3. And then this is a rectangle. That's a 2 by 2. That'll be 4. This is a triangle, width of 1, height of 2. So this is 1/2 2 times 1, which is just 1. So from 0 to 5, this would be -3 times this area, which is 5, 6, 7, 8. So this would be -24. Well, this would end up being +24. Okay. If you want to, you can always work this by, pulling out the constant first, and then if you want to, you can then flip this and make this constant become positive. And this is another way for you to see that it's going to be 3 times +8 to give you that 24. All right, that's it.